So today's topic is electromagnetic fields, and we'll first motivate why we need electromagnetic fields based on a coupled problem of an injection valve, and then we will go in the governing equations, Maxwell equations, look at the different versions because they can be quite tricky to mix up. Look at the constitutive relations we need for especially when we consider Maxwell equations in matter. Of course, in vacuum we don't need any constitutive equations. And then we look at the, for us as mechanical engineers, I would say, a technically relevant case, which is the eddy current case. And then to the special case of magnetostatics. So an injection valve is a typical case where we need electromagnetic fields if it is excited by a coil. This coil, the current in the coil will make the valve move. So we have an interaction between the magnetic fields that produce forces that lead to part movement deformations, so the mechanic field, and of course, if we consider an acoustic fluid also to the acoustic outside. So the injection valve in general is quite complex. You have some pre-injections you want to do a main injection, then some post-injection. And so this is a highly dynamical process. And as I said, we have the electromagnetic field. There we need a subset of Maxwell's equations. We need to consider magnetic nonlinearities, for example, in the material. We have to consider the motional electromagnetic forces if we have currents in moving parts. And the electromagnetic force, as already said, couples to the mechanical PD that describes the deformation of the specimen. The mechanical field then is described by the Navier's equation or the balance of momentum. It has to be considered with contact, so there's an additional nonlinearity involved there. And the deformations of the mechanical field change the electromagnetic field. So because we have moving domains, the magnetic material properties, the magnetic properties change. And if this is vibrating, we can generate sound that is radiating in the environment. So this is a very complex coupled problem. So we have also to consider the acoustical field that can be described by the wave equation, as we have heard earlier. And this is basically the cause of the mechanical vibration. And if the acoustic pressures are substantial, they can even couple back to the mechanical system. Okay, but today's focus is electromagnetics. So how can we describe electromagnetism? This is a large topic, and this diagram is actually very nice because it classifies the different phenomena. So at the top we have electromagnetism described by the Maxwell equations. So this is wave propagation, and then you can split up for high frequencies, you have electromagnetic waves, and for low frequencies we can neglect the wave part and consider electromagnetism that can be either electrostatics, so there's only the electric fields involved, no magnetic fields, and only in the static sense, or in magnetism that can again be split up either in the eddy current case, where only the eddy currents are considered in the time varying sense, and the complete magnetostatic case where we consider static magnetic fields, for example, by stationary currents. Or what quantities do we have in electromagnetics? So these are the ingredients, so to say, the unknowns in Maxwell equations. We have electric fields, electric field intensity. We have the dielectric flux density, the magnetic field intensity, magnetic flux density, a current density, of course. We can have charge densities in our media. We can have magnetizations or polarizations. In the polarizations, because they are very similar, they can be magnetic or electric polarizations. And we have, according material properties, they are given here, but the details will follow in later slides. So here we have written the Maxwell equations. In fact, these are equations not posed by Maxwell alone. There's Ampere's law here in red that relates the curl of the magnetic field intensity to the current density. Then we have Faraday's law, the induction law, so a time-varying magnetic flux density is related to the curl of the electric field. Then we have Gauss' law that we have already encountered in electrostatics. And we have the corrections, and that's the reason why they are called Maxwell equations, that basically connect all these pre-existing equations. So the time derivative of the dielectric displacement, so this displacement current density that Maxwell introduced, and the condition that the B field is divergence free. So now when we count how many unknowns do we have, how many equations do we have? So we have 2 times 3 plus 2 scalar equations. So these are 1, 2. These are the scalar equations. These are the vectorial equations. So 2 scalar equations, 2 vectorial equations give us 8 equations, but we have 16 unknowns. These are our 5 vector valued field, and the Q, this is a scalar field. So to close this equation set, we need constitutive equations. And if you formulate constitutive equations like B is a function of E and B is a function of H and J is a function of E, you have another 9 scalar equations. And that looks a bit overdetermined now, but in fact, you have the equation 44 and 42. They are actually related, so you can take the divergence of 42. If you take the divergence here, the divergence of the curl is always 0. You obtain this equation. Okay, now let's look at the simple case. Let's look at the case of vacuum. So I give a remark here. You have to be careful of the charge density Q and the current density J. They have different meaning in different formulations of the Maxwell equations. So if you consider vacuum, there's no material, there's no matter. The only thing you have are the fields and some charges. So the charge field is also a field. But no constitutive relation, so to say. So you can directly formulate everything in the electric and flux density field because you know the relations in vacuum. So in vacuum, we have D is epsilon 0 times E, so the free space permittivity in vacuum times the electric field, and the magnetic field is mu 0 times H, so the free space permeability times the H field. And then that's all you need to describe the electromagnetic fields. And this is, so to say, called the microscopic version, because if you look in a microscopic sense, you consider matter electromagnetically just as a collection of charges. So you have positive or negative charges, and they make up the behavior of matter. But of course, when you look macroscopically, this is not a very handy description of all matter to describe all charges separately. So actually, we want to have a macroscopic version. But before we go into that, let's look at electromagnetic waves in vacuum. So you can compare Ampere's and Faraday's law to obtain a wave equation. So we have a second time derivative, and we have a second spatial derivative on the vector valued quantity of the electric field density. And you have some kind of excitation term on the right-hand side if you want. And here you can recognize the speed of light, which is the speed of light in vacuum, defined by the vacuum permeability epsilon 0 and the vacuum permeability. This is also a conservation equation we know that needs to hold, but is not explicitly contained in Maxwell equations, but implicitly, of course, guaranteed. And you can basically see this if you take the divergence of Ampere's law and combine it with Gauss' law. So the divergence of the curl is 0. That's why we have the 0 here. So what remains is divergence of the current density J and the time derivative of the charge density, which in fact is a conservation equation for the charge. Let's look a little bit more in detail. When we sort of define the current density as the motion of charges, or velocity field times the charge density at this location, we can insert this and do the divergence of this product. So this is the product rule for the divergence, and then we can actually see that this amounts to the substantial derivative of the charge and an additional term. So this is the typical term we have for one part is the definition of the substantial derivative. So this is this part, and this other part is actually 0, because we can assume that the velocity field has no sources. Otherwise, we won't have matter continuity. So this term is 0. That means the substantial derivative of the charge is 0. So charge is conserved. Okay. Now, when we go into matter, we don't want to prescribe or describe all charges individually. So we want to find suitable constitutive relations. And it turns out not every form of the constitutive equation makes sense physically. There's a specific form that is consistent with Maxwell equations. And this form you can obtain by splitting the charge density into free charges and bound charges. So bound charges are the ones that are not free to move, and the free charges are the remaining ones. So how can we have bound charges? We have encountered this, for example, in the piezoelectric materials already. There the polarization is made up by bound charges. And so the bound charges are described by the polarization of the material, and the definition is that the divergence of the polarization, the negative divergence of the polarization, makes up the bound charges. And similarly, you can do this with the current density. So you say we have free currents. These are the free charges that move around. And we have current densities due to bound charges. So current density due to bound charges are, on the one hand, the polarization charges. So if you change polarization, of course, these bound charges move. That leads to a current or current density. So this is the time derivative of the polarization change. And the other source of bound charges that are in motion are actually described by the magnetization. So the current density of the magnetization current density, Jm, is defined as the curl of the magnetization. So one way to imagine this curl of the magnetization is basically there is an equivalent description of a permanent magnet that is equivalent to a so to say a coil. Okay, and if you insert this definition, what you actually find is a version of Gauss' law that has here the divergence of D, and D must be set up as epsilon 0 E plus P. In fact, PE, so the electric polarization, to not confuse it with the magnetic polarization. And similarly, in Ampere's law, you have the curl of H, and H must be B over mu 0 minus the magnetization. And on the right hand side, you have again the time derivative of B. So this is then the correct, consistent form of the constitutive relations that you need to have. And all nonlinearities, for example, can be contained in the polarization or in the magnetization. Yeah, so we spoke about magnetic material properties in matter. They can be quite complex. So typically, you have the polarization, the electric polarization dependent on the electrical field, and similarly the magnetization dependent on the flux density or field intensity, depending on how you formulate it. So they are in general nonlinear and hysteretic. So hystery dependent, and there's a typical BH curve of a magnetic material depicted here. So you have this characteristic saturation that you encounter. So the remaining slope is the mu 0 slope, and a similar behavior you encounter for the PE loop for the electric properties. So what material models are common and useful? So as a simple case, the linear material behavior. So you say your dielectric field intensity is made up by the epsilon 0 part, and then a part that is described by a relative permittivity times the E field. This can be tensor valued, since we have vector valued quantities in the equation. So two vectors need to be connected by a second rank tensor. And similarly, you can do this with the magnetic relation. So here you call this tensor then the magnetic permeability tensor. If you go to electrodes and permanent magnets, these are materials that have, so to say, an inherent polarization and an inherent magnetization. Then you can, of course, prescribe the value directly. So you have the polarization known, the magnetization known, and you can insert this directly. And in the most general case, you can have, for example, nonlinear curve for the D field. So you can really write this in a nonlinear curve sense, but you should be aware that these curves need to satisfy the physically required large field slope. So the mu 0 and the epsilon 0s should, of course, be contained in this curve. And of course, since this is in general nonlinear, this could also include some hysteretic behavior. In the curve case, no. So in the curve case, you typically neglect the hysteresis and basically condense this down to a curve to have a unique relationship between D and E or H and B. Okay, the final relation we still need is a relation between the electric field and the current density, and this is Ohm's law. So if you consider the Drude model, which models the drift of charge through a material, you can produce the continuity version, so not describing single charges, but charge densities, and you obtain the free charge densities related to the electric conductivity times the electric field. And of course, you can extend this as usual to an anisotropic case for electrically anisotropic material and introduce an electric conductivity tensor gamma. Again, the same argument holds. We relate two vector valued quantities, and this has to be done by a second rank tensor if the material is anisotropic. Okay, so then we can finally write the Maxwell equations in matter as we have already originally posed them with dielectric field intensity and flux density and magnetic field intensity in the equations, but take into account that we have now in matter, of course, different regions with different material properties. So in some regions, we might say these are perfect isolators. In some other regions, we will have electric conductivity that is non-zero, and similarly with the magnetic properties. Okay, so in matter, we of course also have electromagnetic waves, and to show this similar behavior, we take the curl of Faraday's law. Then we assume a linear constitutive law to make this somewhat handleable, so to say. If everything is non-linear, of course, even the electromagnetic waves, they can be very complex. But for the linear constitutive law, we can do this. So we replace B by mu times H. And then we assume that the medium is homogeneous. So we can write a single equation for the whole domain. That means we can pull out the mu from the curl. And then we can use Ampere's law. So replace the curl of H by the current density. And again, we can pull out the material constants and use Ohm's law to replace the free currents by the electric field. And what we have obtained is an equation only for the electric field. And again, we can see the typical structure of a wave equation. So we have a double spatial derivative by the double curl. And we have a double time derivative here. And we have a single time derivative, which actually damps our waves. And in fact, you can obtain a similar equation for B in a very similar matter. Just to highlight this, from the wave equation, you can read off the dispersion relation for electromagnetic waves. And you can use this dispersion relation that actually relates the frequency and the wave number to compute the electromagnetic spectrum. For example, in vacuum, this is the typical diagram, and if we look at the frequency scales that we encounter in engineering, so let's look at our frequencies. We are maybe in the kilohertz regime, 10 to the power 4, 10 kilohertz. we are for free space waves in the long radio wave range, so the wavelengths are kilometers long. Of course, this holds for vacuum. For matter, the wave speeds and wavelength, of course, can differ. And this is, of course, the isotropic formulation. Good. So now we want to get to the eddy current case. So this is the simplification that is typically relevant for mechanical engineering, so to say, and I guess for a large part of electrical engineering. So whenever waves are not relevant and we still have time varying fields, we are in the eddy current case. And this we obtain by simply setting the displacement current density to 0. And then we have the eddy current case, and what this does is it decouples Gauss' law from the equation. So electrostatics is out of the question. Now we look at the eddy current case. So these are the three equations that remain, and this eddy current case is typically useful for frequencies below 10 kilohertz. The argument is based on the wavelength. So if the wavelength is large compared to the domain we're interested in, then we won't see any wave because, well, we don't see any variation in amplitude. We don't have to consider them and are fine with the eddy current case. So this is why the wavelength approximation, so to say, is important to know when the eddy current case is relevant. Yeah, and as I already said, Gauss' law is decoupled. We have a few interface conditions between the fields when we consider different materials. And to derive these interface conditions, it's useful to write the equations not in the differential form, but use Stokes theorems, for example, to bring them in integral form. So when you take the divergence-free condition on B and you use the divergence theorem, you obtain the following equation, and then you can try to build this second integral, so the surface integral over basically the top and the bottom of your interface. So you make a little cube that is very thin, depicted here. The thickness B of this cube goes to 0, and then we know that the integral over the whole surface needs to be the integral of top and bottom surface. And if you insert this, you see then that the normal component, which are effective in these integrals of the magnetic flux density, need to be continuous. And similarly, you can do this for the Faraday's law also. So here you use Stokes' theorem to reformulate the curl of H into the surface integral. And then again, you want to build this surface integral. And there you see that the surface integral is made up by the tangential components of H, written by the cross product. And they don't necessarily have to be continuous. They are not continuous if you have a so-called surface current at the interface. So this would be somewhat a special description of a current density. Of course, you don't have infinitely thin sheets of material in reality, but this is a concept. So if you have surface currents as a concept, then you also have a jump in the tangential component of H. If you don't use this concept, you know that the tangential component of H needs to be continuous over material jumps. And these interface conditions we will see for the finite element formulations are essential to get physically correct formulations. But that's not the topic now. We want to look at the eddy current case and to a bit visualize what is important in the eddy current case. We want to look at what is the skin depth and eddy currents in general. And a good example for this is to try to attempt an analytical solution for this. So in general, magnetic flux through a conducting loop will introduce currents and the corresponding voltage. And when you have alternating currents, you will see that the current density that is introduced actually likes to concentrate at the boundaries of a conductor, and this concentration is larger and larger the larger the frequency gets. So this is the skin effect, so to say, and to see this in equations, we will start from the governing equations and first write them for a special case of an infinite half space. So we have a half space that we consider. We have magnetic fields that are pointing into the blackboard, and normal to that, orthogonal to that, we will have the electric fields. So then you can formulate the equations in a scalar sense. So you have the H components, so the magnetic components in Y direction pointing into the blackboard, and in X direction we have the current density component, and also the curls simplify to normal derivatives in Z direction. Okay, yeah, linear constitutive equation, so Ohm's law and the permeability for the magnetic behavior. And if you combine all of that, what you obtain is this diffusion type equation where you have a second time derivative, second spatial derivative, and a single time derivative. And you can obtain this equation for H. Of course, there are equivalent formulations, equations that you can derive for all the other quantities. So how do we solve the diffusion equation? The answer is given here. So we're interested in the solution for harmonic excitation. So we make the harmonic ansatz of a complex valued quantity times e to the power of j omega t. Bring this into the equation so we can build the time derivative, and what remains is ordinary differential equation in H, Hy. So we can build the characteristic equation, solve for the roots. These give us the number 1 and number 2, where we have the material parameters inside. And with these roots, we can write the general solution for the problem. And in order to determine the coefficients now, we have to think about the physical behavior. So the fields should remain bounded, making the C1 0, and the second C2 can then be obtained from the field condition of the excitation. Okay, yeah, so this is the general solution that we can then obtain with the boundary condition. So at Z equals 0, we want to set a certain value of H. This could be from the outside field. We have seen that the tangential component of H needs to be continuous. So we have some H outside. This needs to be present at the boundary of Z equals 0. And then we have this funny decaying exponential that we've actually already seen in the linearized flow equations. This is similar to the Stokes boundary layer. And to make this expression a bit easier to write, one introduces the skin depth delta, and this is the equations for it, so it depends inversely to the frequency and to the two material parameters, permeability and electric conductivity. And of course, the physical quantity, to remind you, is always the real part of these complex valued quantities if you make a complex valued ansatz. And so you can write it also as a cosine if you want. And then you have equivalent expressions for B, J, and E. You can obtain them from the original equations by just inserting the single solution, or the other way, of course, is to derive the initial differential equation for a different quantity. Yeah, so here are the expressions, and you see they are completely the same. So all fields decay with the same eddy, with the same skin depth. What you can also see a little bit is that in this formulation, you see the phase here that changes with respect to the z coordinate. So you have different phases which correspond to waves, evanescent waves propagating into the domain from the boundary. Okay, so now we want to solve the eddy current problem, and typical strategies for this are to introduce suitable potential functions. And one set of those are described here. So the magnetic flux density can be described by the magnetic vector potential defined such that the curl of the potential is the magnetic flux density. And you see that this identically satisfies the divergence of B is zero, because the divergence of the curl is always zero. So by introducing this potential, it's nice, we get rid of one equation because we know it's always identically satisfied. And then you can insert this into Faraday's law to obtain the curl of E plus the ADT is zero, which is identically satisfied if you introduce the E field such that it is a gradient field, and in addition the ADT is also there. Because again, the argument is the curl of the gradient needs to be zero. And then you can use these two definitions, insert them in the rest of the equations, and you obtain the PDEs that you need to solve, and you need to solve them then for A and phi, which is less degrees of freedom. This is only a particular case, so there are different potential formulations that might be suitable for different formulations. So Oscar Biro has a nice publication summarizing a lot of potential formulations, especially regarding their finite element implementation. Okay, then we also have to consider that we have these different material domains that we need to consider. So we have electrically conductive regions where we can have free currents, and these can be two types of free currents. So either they are already known, so they are prescribed, for example, by coils, or they are unknown in conducting materials, so they are eddy currents. So these are the two things you can have in electrically conductive regions, but you can't have both of them at the same time. So either you know the current density or it's unknown and it's eddy currents. Then you can have electrical isolators. So they only have the magnetic material behavior and the conductivity set to 0. So if you want, this would be a special case of an eddy current region with 0 conductivity. And you have the magnetic materials that have, so to say, different properties than the free space permittivity, permeability. So you can have linear, non-linear behavior, or you can have a constant magnetization, for example, in permanent magnets. And typically these different regions are not mentioned when you see the description of the eddy current problem. You just say, okay, this is what we have, but typically you have current densities not in the whole domain, but only in subsets. And you have eddy currents not in the whole domain, but only in subregions where you actually have electrical activity. Good. How can you model current density? So if you have a coil, in practice, of course, a coil is made up of a lot of windings, but these are difficult to model in detail. So what one usually does is one uses so-called stranded coils, where you homogenize the current density in all the winding and say, okay, we have a constant current density over this whole region. And in this region, we can't have eddy currents because the eddy currents would need to develop in the single wires because the wires are isolated against each other. The eddy currents cannot develop. Of course, this assumption is only correct for frequencies where that are so low that not eddy currents in the individual wires get important. And to compute such a eddy current density, you can compute it, of course, from the total current in the wire from the number of wires. So you have to multiply them to get the total current. And then you have to divide by the total area to get the current density. And typically you use some kind of filling factor. You say, okay, we don't have wire in all the region, but we also have to account for the isolation layers. So this increases the current density a little bit. And the direction is given, so to say, by the direction of the winding. So if you have a circular coil, of course, you have to give the scalar current density value also a direction to it. So these were the coil regions. We can also have eddy current regions. And these are the regions where the free currents correspond to eddy currents that are not known but want to be computed. And in this region, the eddy current density must be satisfy the continuity equation, which is implicitly done by Maxwell equations and also by the eddy current problem. So this is nice. And in this region, we assume Ohm's law. So you will simply say the eddy current density is related to the electric field density times the conductivity. And this actually brings you to the A star formulation for the eddy current problem. In this formulation, you don't need the electric scalar potential. So you can set B equal to the curl of A star and E equal to the time derivative of the magnetic vector potential A star. And then you can insert the linear material law and obtain a single PDE for the magnetic vector potential. These are two equations here because I've explicitly separated out the regions. So of course you could just write a single equation. These are actually subsets, so you could put the Ji in the first equation and write it over the whole domain, but then you don't have this clear separation that in regions where you prescribe a right-hand side impressed current density, you can't have eddy current eddy currents anymore. And in regions where you have eddy currents, you can't at the same time prescribe an impressed current density. And then the more complex formulation is actually the AV formulation, where you take into account the V, so the electric scalar potential. So we just insert these into Ampere's and Faraday's law, and we don't have to write the continuity equation. In this case, we have to write the continuity equation explicitly, because this is the equation that allows us to compute the electric scalar potential phi. So the first equation is similar in the sense that we have again the curl term for A, but you also have the electric scalar potential term here. We don't have any impressed current density here, because in this case you can actually do the excitation by a so-called electric ports. We haven't spoken about boundary conditions too much yet, only on the field equations, but of course these equations need boundary conditions like every boundary value problem, and here the forcing can be introduced via the boundary conditions on the electric scalar potential. Yeah, and then we have another relevant special case, and this is the special case that we encounter if we neglect all time derivatives. So we consider a time-independent problems, and if you, for the sake of simplicity, take linear material behavior, you have regions where you can prescribe magnetization. So that's the last equation, the curl of A is equal to the curl of the magnetization. You can have regions where you have prescribed impressed current densities, and you have regions where you have none of the above, so you only need to satisfy the double curl equation, again with the material parameter inside. And in fact, this is the equation set that you also encounter if you have no electric conductivity. So the eddy current case that we have seen beforehand, if you set any electric conductivity to 0, you encounter this equation set, which also tells you that you, in this case, don't need to consider equation. These are actually subsets, so you could put the Ji in the first equation and write it over the whole domain, but then you don't have this clear separation that in regions where you prescribe a right-hand side impressed current density, you can't have eddy current eddy currents anymore. And in regions where you have eddy currents, you can't at the same time prescribe an impressed current density. And then the more complex formulation is actually the AV formulation, where you take into account the V, so the electric scalar potential. So we just insert these into Ampere's and Faraday's law, and we don't have to write the continuity equation. In this case, we have to write the continuity equation explicitly, because this is the equation that allows us to compute the electric scalar potential phi. So the first equation is similar in the sense that we have again the curl term for A, but you also have the electric scalar potential term here. We don't have any impressed current density here, because in this case you can actually do the excitation by a so-called electric ports. We haven't spoken about boundary conditions too much yet, only on the field equations. But of course, these equations need boundary conditions like every boundary value problem. And here, the forcing can be introduced via the boundary conditions on the electric scalar potential. Yeah, and then we have another relevant special case, and this is the special case that we encounter if we neglect all time derivatives. So we consider the time-independent problems, and if you, for the sake of simplicity, take linear material behavior, you have regions where you can prescribe magnetization. So that's the last equation, the curl of A is equal to the curl of the magnetization. You can have regions where you have prescribed impressed current densities, and you have regions where you have none of the above, so you only need to satisfy the double curl equation, again with the material parameter aside. And in fact, this is the equation set that you also encounter if you have no electric conductivity. So the eddy current case that we have seen beforehand, if you set any electric conductivity to 0, you encounter this equation set, which also tells you that you, in this case, don't need to consider any time dependence.